Hello and welcome to the first video in Mathematics 2. In this video we're going to introduce a new topic, and that is differential equations. Differential equations basically relate a function to its derivative or its derivatives of higher order possibly. We'll start with a very simple case here and just regard a function and its derivative. We're going to see how to solve problems of that kind. And we'll also see a simple example of where problems of that kind may appear. So this introduces a new chapter. This is chapter 11, Differential Equations. And we'll start with an introduction. So 11.1, Introduction. So what we did previously in analysis, in the chapters on integration, we also had a relation between a function and the derivative. And the idea here was, given some function g, can we find a function where the derivative of that new function is g? So in other words, we were looking for the antiderivative of g. Okay, so that was a setting that we dealt with previously. Given a function g, usually from the reals to the reals, the task was to find an antiderivative. And that is a function f, again from the reals to the reals, with f prime of x equals g. So what we did was we established a relation between a function, a given function g, and the derivative of a different function f. What we are now going to do is we're going to establish a relation between a function and its own derivatives. And that is what is called a differential equation. So now, relation between a function f, we'll usually assume, again, f is a function on the reals, and its own derivative, f prime. So the task is to find a function that satisfies this relation. Find a function f that satisfies such a relation. And this kind of relation, that is known as an ordinary differential equation. Now in this case, we will only talk about ordinary differential equations. I'll briefly mention the other kind later on, but basically that's the only thing we're going to deal with. So I'm just going to abbreviate this by DE for differential equations. Let's see a brief example before we try to get into the theory of how to solve these things. And the example that we are going to see is capital accumulation. The question here is, we want to describe how an investment grows over time. So let's say you have a certain capital stock. You invest that, so there is a factor that either increases or decreases that capital over time. Usually that's interest, or maybe inflation if you want to decrease. And of course you have the option to invest at certain times. And the question is, how does this dynamic change your capital? So what's the change rate? How is that related to the capital stock? How is that related to the external factors like interest, and of course to your investments? And then of course, if you can determine that, if you can come up with a relation for that, you want to know how your investment actually evolves. So how the capital stock grows or shrinks over time. Okay, so we'd start with a very simple example here. Let's say we have a capital stock at some time t, and we are going to denote this by k of t. Then we have what we just call the accumulation rate. That's the rate of change of that capital stock over time. Usually that's interest or inflation or something like that. We'll call that delta. That's just a real number. And then we have the option to make investments. So the investment at time t, this will be denoted as I of t. And we want to relate the change rate of the capital to these factors here. So the change rate of the capital, that is k prime of t. Change rate of k at time t. And well, how does the capital change? Well, of course, it changes according to the accumulation rate and the current capital stock. So that is delta times k of t. And then it also changes according to the investment. So if you invest, then of course there is a change in capital. And there can also be a negative investment, meaning you take something out of your capital stock. And of course that also leads to change. So this is the function that we are looking at. K prime of t equals delta times k of t plus I of t. How can we find a solution for this differential equation? How can we find a function k that solves this relation here? To find out, we are first going to look at a simple case, the so-called homogeneous case, where there is no investment. So we have a differential equation that just relates k and k prime and some factors, but no factor that does not involve k or one of its derivatives. Okay, so that is case 1. The so-called homogeneous case. So we're going to look at homogeneous differential equations first. And that means I of t equals 0. So in this case, what we have is k prime of t equals delta k of t. So we're looking for a function that satisfies this differential equation, meaning basically the derivative of the function is the function itself times some constant. And you hopefully all know a function that has this precise property, and that is the exponential function. So the claim here is a solution for this is k of t equals e to the delta t. And more precisely, we can also multiply this by any constant, because that constant will be in k and also in k prime. So that will just cancel out. Okay, so we have gamma times e to the delta t where gamma is some constant. Well, that's the set of all possible solutions for the homogeneous system, actually. Now one can show that under certain conditions this solution is unique, so there is no other possible solution. We won't go deeper into that fact, but you just should know how to solve a differential equation of this type, and that is this way. Okay? Let's quickly verify that this actually does solve our differential equation. So let's compute k prime. Now k prime is gamma times delta times e to the delta t. So we get exactly delta times k of t. And that means we successfully solved our differential equation here. So the homogeneous case seems easy. And again, to sum this up, the set of solutions for the homogeneous differential equation here is the set of functions gamma times e to the delta t, where gamma is some constant, some real number. Now, how about the inhomogeneous case? How about if we have some investment function that is not all zero? Let's look at that case next. So that's case 2. The inhomogeneous differential equation. What we mean by that is we have a general function I of t that is not necessarily zero everywhere. Now what we do here is a two-step process. We'll first use the fact that it is sufficient to find one particular solution of that inhomogeneous system to get all possible solutions. So step 1, it is sufficient to determine one so-called particular solution of the inhomogeneous differential equation. The set of all possible solutions is then obtained by using this particular solution and adding a set of all solutions for the homogeneous system. This should sound familiar. We did the same thing for linear equation systems. You remember that? To solve a linear equation system, what we could do is solve the homogeneous system, then determine one possible solution for the inhomogeneous system, and adding this solution to the set of all solutions for the homogeneous system gave us a set of all solutions for the inhomogeneous system. Okay? Same principle here. It's sufficient to determine one particular solution of the inhomogeneous differential equation. Okay? Now, why is that the case? Let's have a quick look into that. Say we have a solution KH. That's a solution for the homogeneous differential equation. Well, that means KH prime of t equals delta times kh of t. And we have a particular solution kp of t. That's a solution for the inhomogeneous differential equation. And that means kp prime of t equals delta kp of t plus I of t. So if we combine those two, what happens? So what we do is we set kt to kp of t plus kh of t. Then what is the derivative of k of t? So k prime of t, well, it's obviously kp prime of t plus kh prime of t. And because these are solutions, we get that k prime of t equals delta times kp of t plus I of t. And kh prime of t equals delta times kh of t. Okay, so what we have is, this is delta times kp of t plus kh of t plus I of t. So delta times k of t plus I of t. And that means k actually is a solution for the inhomogeneous system again, right? So adding this homogeneous part didn't change the solution property. That means we can get all possible solutions this way. Okay, so that's the principal idea. Now the question remains, how do we get a solution for the inhomogeneous system? So that's part 2 here. We need to determine one possible solution. For the inhomogeneous differential equation, and we're going to do this through a technique that is called variation of constant. Okay, now that name might seem a little paradoxical at first, but that's actually precisely what it does. What we do is, we already know that for the homogeneous system, we have a solution that looks like this. K of t equals some constant times e to the delta t. And now we just make an ansatz by saying, well, let's use this kt, but instead of the constant, let's use some arbitrary function. And using this function, we'll hopefully be able to capture whatever this I of t, this inhomogeneous point, does. So let's use some function c of t in place of that gamma. Okay? So this is the variation of constant part here. Right? That's now a function that we need to determine. And then what we do is we substitute this into the differential equation. Substitute into dE. Okay, so what happens if we compute the derivative of k? Then we're using the product rule of differentiation. We get c prime of t times e to the delta t plus c of t times delta times e to the delta t. Okay, so that's k prime. And that needs to be the same as k times delta plus I of t. So with our ansatz, what we have here, this here is actually the same as delta times k of t. So we have that part here already. So that means what is left here is c prime of t times e to the delta t. is equal to I of t. And now we can just solve this for c. So that means c prime first. C prime is then I of t times e to the minus delta t. And that in turn means c of t is the integral over this expression, e of t times e to the minus delta t dt. We do know how to compute integrals, so computing a sufficient function c of t should not be too hard here. Okay, so that's what we're going to do. And of course, depending on how that function I actually looks like, it might turn out to be very hard to compute that integral. But in principle, this is something that we can do. Okay, so that's how we solve differential equations of this type. We'll see an example for that in one of the next videos, where things will hopefully become clearer. So to conclude this video here, let's sum up what we learned so far. Quick summary. We were dealing with differential equations of the type, and I'm now going to use a more general notation that is encountered very often in practice. I'm going to denote my function by y. So we have a function like y, and a differential equation like y prime of t equals some constant delta times y of t plus some inhomogeneous part I of t. And how do we solve that? Well, we first solve the homogeneous differential equation, determine the set of all solutions to that homogeneous differential equation. Determine all solutions to the homogeneous differential equation. That homogeneous equation is y prime of t equals delta times y of t. And you know that set of solutions is some constant gamma times e to the delta t, and gamma is some real number. That's the solution set here. Then, as a second step, we determine one particular solution of the inhomogeneous system through variation of constant. Determine a particular solution to the inhomogeneous differential equation through variation of constant. Okay, what we do here is we use the ansatz y of t is equal to some function c of t times e to the delta t. And we substitute this into the differential equation and determine the function c. So substitute into differential equation, determine c of t. And that gives us a set of solutions to the inhomogeneous system. And that set of solutions is then our particular solution, c of t times e to the delta t plus gamma e to the delta t, and gamma any real number. Right, so this is the particular solution here. And this here is the set of solutions to the homogeneous differential equation. And finally, one more step that I did not mention yet. In many cases, there will be some initial conditions given, like for example, the capital stock that you start your investment with, the capital at time 0. And these can then be used to single out one solution in that set that we are actually interested in. So in other words, we can determine all the constants that are contained in our set of solutions using these so-called initial conditions or initial values. So just mention that, use initial values to determine constants and single out the one function that accurately describes the situation at hand here. We'll see an example about that in one of the next videos that hopefully makes this a little clearer. Okay, so far about the introduction to differential equations. Again, we'll see an example in one of the next videos, and then we're going to dig a little deeper and have a look at systems of more than one differential equation. Yeah? Like we did with systems of linear equations, we can also consider systems of several differential equations that need to be satisfied at the same time. And that's what we're going to do next. Thank you.